Hello everybody and welcome to a new episode of Data Analytics Computing. Follow along. In this case, we're going to go over multiple linear regression with Python. In a small change compared to other videos, this video is going to build onto my linear regression video. So I will not be covering a ton of programming concepts that I already covered there. In case you feel lost, please go back to that video that will be somewhere around here or in the description, and then come back. All right, in this video particularly, we're going to focus on how to extend the linear model from one predictor and one prediction to multiple predictors and one prediction. We will be looking at more advanced programming concepts as well, and if you have any questions, as always, just put them in the comments. First of all, we need our packages. We import pandas, NumPy, scalar linear model, and matplotlib pipeline. After importing that, you can always just install them as always with these lines of code over here. You will just need to execute them either in the console or in your environment. Now, we are going to look again at the accidents data frame. As a reminder, this data frame that we already looked at in the random forest video is looking at the accidents that happened in Arizona. This code here helps us offsetting it as always. We just want these columns of the data frame. Now, a little bit of context here. We are going to be using payrolls as our prediction. This is how many people died in the accident. We will be using every single other variable to try to predict how many people are going to die in a given accident. We'll go ahead and subset this. And as you can see, it has only 5 columns instead of the 80 of the original one. Here you have a brief description of every single predictor here. Persons is the number of persons who were involved in the accident. Indian reservation tells us if the accident happened in an Indian reservation or not. A thought is the time of day, and a thou is the day of week. So we always need to see if there is any nulls here. We're going to go ahead with this. And luckily, there is no nulls here. We don't need to drop any values as we're going to just go over each of them. We can just go ahead and proceed. Compare this to other parts of the videos where we needed to drop the nulls because sklearn cannot handle the nulls. Now, there is something I want to emphasize here before I go into this data frame here and this while loop here. We could use unique to get the values of one single column. We can do that. However, we want to do it in a smarter way. Instead of doing it step by step, we could just take one column and then put unique, and then the next one, put unique again, etc., etc., etc. We can do something a little bit smarter by looping through the index. In this specific case, we're going to use a while loop. Now, there is a lot happening here, but I don't want to lose you here. First, we are going to execute this line of code. This just tells us what are the columns in the index here, what columns we're looking for here. I equals to 0. This is an index that we're going to be using at. Pay attention to the value, but right now it's 0. Now, there might seem that there is a ton happening here in this while loop, but there is not a lot, being honest. I'm saying while the value of I is less than the length by length of how many columns are here, first print the accidents df subcolumn I, so this value here, plus a string that says unique values. And after that, print me that actual column, the unique values, but subsetting it by I. Before I execute this, in case I have lost you, just hear me for a second. First, let's take this chunk of code, len accidents df that columns. What is that going to give us? 5. Now, what happens if we get rid of the columns part? We are getting the actual length of the data frame. We need the columns method in order to get the 5 columns that we have over here. And as we have seen, there are 5 columns, and they're in this order here. Now, let's start by just taking this path, AxiosDF, subcolumns I, and let's replace the I with a 0. Persons, because we are taking this AxiosDF sub, and then from the columns method, we are taking the first value. Python starts at 0. Some programming languages start at 1, but Python just starts at 0. We could do this with 1 instead, or with 2, and you see why. We are just going through each of these column names here. Now, what about this? ilog. This is a new method that we haven't used yet. What ilog allows us to do is basically this. It is going to return us the actual data inside it. But you might be asking yourself, why I can't do this instead? Let's just get rid of ilog, put this into string, and the persons. Well, you would be right. It's exactly the same thing. There are some reasons why in this video we're using ilog, mostly because I want to show a different way to do it. And in this case, it's very convenient because we have I. We need that I, the same I that is here, in order to loop through it. We could have just decided to do this code with 0 here and the name of the column 4 times. But instead of that, what I'm going to do is execute this chunk of code independently. Finally, something that we want to be aware is this I plus equals 1. This I plus equals 1 adds 1 to the current value. It is the same as writing I equals I plus 1. Now, what is the value of I? 0. If we do I plus 1 equals I, will be 0 plus 1 equals 2. Equals 1, actually, my bad. But equals 1. So 0 plus 1 equals 1. Therefore, 1 is going to be the new value of I. When you do 1 plus 1, whenever the value of I is 1, it's going to be equal to 2. And therefore, it's going to increase. Why we do this? While loops execute as long as there's a condition here. If I didn't have this condition, it would just go infinite into a loop until it found the end of the data frame and it just errored out. Now let's go ahead and we can execute this while loop. Now, what do we see here? We first get the person's unique values because we did that. We said, print me the first column with I equals 0 plus unique values. And then you're going to take the unique values of that column. We can double check that actually. Just take this and let's replace I with 0. There you go, exactly the same result. We just did that to get all the values. Same with Indian reservation, payrolls, ATOT, and ADAO. This is one of the biggest and most powerful concepts of programming languages. We can iterate through a list, and we can use that to do a lot of stuff. This is a while loop. There are for loops too. Python has a ton of looping documentation. I'm just scratching the surface here, but I want to show you how for data analysis, this is a very powerful tool, because even though you can only apply something to a specific column, we can iterate through all the columns of values. And part of the magic of this is, let's say we added one more variable to this. Well, it's fine, because I is just going to increase until the length of the how many columns are there. If there is one more column, it's just going to go one more. And now let's just triple check our value of I before we move on. As you can see here, I is equal to 5. Now you might be asking, can we still run this loop? We can try. It is not going to return us anything. Why? Because this condition is not being met. I is not less than the length the length of the columns in the data frame. There is a very easy way to fix this though. We just need to make I, instead of equal to 5, equal to 0 again. And now when we do our while loop again, we are going to get the same result. This is an idiosyncrasy. You could have done a for loop for this. I just want to show different approaches. And there are more elegant ways to do this, but this is just a good way to show the power of programming and looping in general. Now that we have done that and we know the unique values, see how persons is a continuous variable. Indian reservation is just 0 or 1, yes or no. Was it in Indian reservation? Yes, 1, if not, no. Fetus is a continuous 2. It shows us how many people died in the accident from 1 to 5 here. So the A and ADAO are a little bit more complicated to find out, but Todd basically tells us what the time was, if it was a daylight, if it was at night, or it was something in between. And DAO literally tells you what's the day of the week, if it was a weekend, if it was a weekday, or something else. You can see more in the documentation if you go into the metadata that is provided in Kaggle. Now we go ahead and declare our X. As you can see, X is everything besides fields. We are dropping that as a column here and just saying take everything else from this accident DF. That's why it's only 4 columns instead of 5 here. Our Y is going to be fatals because we want to predict that. We import linear regression from sklearn, as we have seen multiple times. We could give this any name. I'm just giving this linear model because it's the most convenient one for me right now. Now we're going to feed the model not only on 1, as we did in our previous video, but all the variables of X. We are not performing train test split because this video will become too long if I do it. It will come into a future video. But you want to know that what we said in random forest applies to this too, more so than to the random forests. Linear models are very they are very sensitive to outliers. You want to be sure that you're not capturing only noise or outliers in the linear model. And there are more advanced techniques to do this, and this dataset might not be a good demonstration of it, but I just want you to be aware that that exists, and you want to look out for it whenever you're feeding a linear model, and more so when you're feeding a multiple linear model, like in this case. Luckily, sklearn does not care how many variables X has. In our previous video, we actually did a special case of it, but here we can just feed X and Y. As you can see, the syntax is rather straightforward. We can get our score, the R squared for this model, 0.16. Now, this is not as awful as it could be, but you will see soon why this data is not suited for linear regression, particularly speaking. Can we plot this? Not really. We cannot plot multiple linear regression model, at least as easily as we did with our actual linear regression models. Now, why? There's multiple reasons why, as you can see here. It is not a line like we see in simple linear regression. This is a hyperplane. You will see soon that this looks like a plane in multiple dimensions, optimizing through all of them. We can still get some information though, like intercepts and coefficients, but more advanced hypothesis testing can be performed only using the Python package stats models that I may cover in the future, but for this video, sklearn is good enough. Now let's go ahead and just see what is the intercept of this. 0.89. What is this? If we look at our data, this is saying if all your predictors were 0, your prediction would be this. What does this mean in this case? If there are 0 persons, no Indian residents, 0 ATOL and 0 ADAO by the coding, then this is how many people will die for the fatalities for that accident. Obviously, that might not be possible because if there are 0 persons involved in the accident, there's obviously not going to be anybody that can die by the accident. And this is something that I also want you to see. The model will feed the data as you give it to it. Therefore, you will get something. But how accurate that is depends a lot on your business understanding, or in this case, about fatal accidents, on the subject matter experts that you are relying on. You just want to be careful because, again, this is not possible. If there are no persons involved, nobody can die in the accident. You just want to think twice. And this is why we retrieve these things, because we don't want to just get a huge black box that tells us this is how you can fit this. We also want to know if that makes sense. In this case, the model might be useful for some exploration and to see and to predict some accidents in general case, but we would not be able to use it when there is no persons involved, for example. Let's find the coefficients of the model. We get an array. Now, what is this? This is giving you, and it's going to be more applicable if we can use to this. What are the coefficients for each predictor here? So for persons, this is the coefficient. For Indian residents, this is the coefficient. For A thought, this is the coefficient. And for A DAO, this is the coefficient. Notice how for A DAO, this is negative. This is basically saying there is a negative relationship between how many people die and the earthquake. Again, it really depends on the encoding. I will not cover dummy variables in this video either, but just be aware that these 3 are dummy variables, and we will see soon why. Now, this is not really that informative, but with another while loop, we can get, again, what we just did here. How we interpret this coefficient in a more rigorous way? If you have taken a statistics class at a college level, you should know that there is a strong relationship being implied between the predictors and the prediction. Again, you may know these as dependent variables and independent variables in the statistics world instead. Here, though, we can get a similar inference than in simple linear regression, but we need to keep all the other coefficients, all the other predictors as they are right now. So, for example, given a 1 unit change on one predictor, everything else staying the same, the response will change by the coefficient pretty much. Why is this? There is a strong assumption of independence in the linear model. This is one of the most important assumptions in linear regression that I will not cover in depth. That's why you have an introduction to statistical learning and multiple other resources. And I may also cover it in some video. But the linear model is assuming that there is no relationship between these 4 variables. In the real world, there is obviously. How many persons are involved might be related in some way to an Indian reservation, because obviously some Indian reservations have more people or less people than the rest of the state of Arizona, and there will be at least a weak correlation between them. Same with A thought and A DAO, but for this problem, this is just something for you to be aware of. Now, let's go ahead and use a while loop. We already did this. We know what coefficients are related to what column on X, but we can do a smarter approach. It is just nice to double check yourself, because when you are doing a ton of manual coding and you're repeating yourself a lot of times, you may just make a typo. All of us are humans. You may just forget about something. So when you can just automate it, that's a pretty powerful skill to learn as well. In this case, we are declaring a new index called I2, and that's going to be 0. That's our variable that we're going to be looping on. What is this? Don't scare yourself. I won't go into detail about it, but f in the print function allows us to put a variable inside of the printing. Now, let's recall a little bit. What printing does is just putting something to the console. So if I do this, print I2, I just get 0 because what is I2? It's 0. This is actual text that is being outputted by the console. This is not. This is just what the console is proceeding. That's why you have out 33. Now, F allows us to do this. So what if I do this only though? Let's say if I just take this and I put it inside the print. I'm going to get this fancy model intercept. Why? Because print does not know what to do with that, but it's a string, it's inside the string. Therefore, I can just output it there. However, if we take this instead, with the F, see how it changed columns. This is not a string anymore. And I forgot a parenthesis there. But this is the actual variable. So I basically got model intercept, and then I get the value of the variable. I'm not getting only the name of the variable as before here, but I'm getting the value inside it, what this actually is represented here. There is a lot more to F, and there is a ton more formatting that you can look at in the print function documentation. But I just want you to be aware, this makes our life easier. And again, there is a lot of other ways you could do this. This is more of the placeholder way to do it. You could just add it as string instead. With any programming language, there is probably 10 different ways at least to do something. This is just a way I want to show you, just to put into perspective. There are more ways to print output than you can think of at the first second. Now, we will do the same thing that we did before. I2, while this is less than the length of how many columns it has, first go ahead and print that column name. And then you're going to say coefficient. After that, print the coefficient for that specific predictor. And then just do the I2 plus equals 1. Notice how print is not inside this while loop, and this is something important. Python organizes the code with indentation. This is the reason why this is indented. If I do this, you can see how I get an error from here from Python. It's telling me that there's an indented block. Why? Because I have a while loop. It's expected. That's how you can know when something is part of a chunk of code or not. This not only applies to for loops, but to functions and functional programming in general, that I may go more in detail someday in the future, but not. Let's over print first, and then follow it by the while loop. Here you go. This is not the best formatted output ever, but it is an output. You first get what's the model intercept here. Then you get the Persis coefficient, that is this one. Indian reservation coefficient, this one. A Todd coefficient is this one, and A Dow coefficient is this one. Now we could make this way prettier. We could have added a title, we could have added more spaces here. But I just want to show you again that this is a way for you to not need to do the manual work instead, and just use the programming advantages of Python in order to make a more structured and standardized code. Once I have this code, I can just run it, and it will basically just accept me whatever X I am giving it to it, as long as X is consistent with itself. Now, you may be asking from the while loop that we worked on before, can I run it again? Nope. Why? Because I2 is now 4. Why is I2 4? because I just put I4 to the number of variables in X, that is 4. Compare that to our whole data that we did against the F sub that has 5 of them. That's why I stop at 5 and I choose 4 instead. But that's easy to fix. We can just make it back to 0 and loop over again. And there you go, that's our output. There are ways to visualize regressions with true predictors in 3D plots. However, they are actually rather cumbersome and outside of the scope of this video. I will leave a link on the description to how to perform that if you're interested, but it relies on a 3D package as well. However, we can do something a little bit different. We are only feeding each of these predictors to our prediction independently. We are not doing a whole regression between each of them in a ton of different models. For that, we'd rather just do a correlation matrix. But we can just feed them separately. So this is going to be a lot of repetition, but here you can see we are creating 4 additional models, each of them with its own instance of linear regression. You can see here, I have my actual linear model, that is the one that I feed in all my X. And I have each of these 4 ones that I just declared, and I haven't fitted them yet. Now, what is this? This is nothing more. If we take this over, I want to take a second to go over this part of it. What this gives us is an array in a specific format that sklearn likes. Now, if we go a little bit back and we just get rid of the reshape, we get this array instead that is in a little different shape. Now, what if we just get rid of the values part of it? We get this that is a list of the persons column in the data frame. Why is this important? Well, we cannot fit this into sklearn. There are some limitations on why we cannot do it. I won't go into them again. But again, this thing is same as saying X persons. It is exactly the same. We could have done X persons, that values to get the values of it, and then that reshape to get the actual shape of it that we need to in sklearn, and then get Y. Why I did not do that? Because again, I just want to show you that there are different ways to do this instead of just doing it all the way through X persons. But again, nothing wrong with doing this approach on just look at X and the column inside it. This is the most intuitive way, but ilog allows us to use the index number. What column number is this one? We're going to go ahead and feed all of these models. So again, each of them is being fed into a different column. But besides that, everything else is the same. It's just a ton of repetition. We could do a loop with this. I'm just not going to do it because it would be cumbersome, especially because you have a different name for each model. There are ways to do this though, and you could do it in a more refined way. We just did that. As you can see here, there is just 4 linear regressions. So this is not an actual output, but it's just telling you this is done. And this will be more obvious if we were not using an IDE like Spider. If you were just using the console, you would see the difference more obviously between print and when the console is just returning you something to tell. I am just returning you to tell you this is done. Now, we are going to use F again in each of the models. So this is a lot of repetition again. First, let's print the score model. We already talked about F. F just allows us to put a variable or a variable with a method inside here and get the value of that. Then after that, we are going to print what that value is and then the intercept and the coefficient. We can go ahead and do that for the first model. So this is the score of the model here. This is the intercept of the model here. And this is the coefficient of the model. See how, because I have 4 prints, I have 4 lines. Each of these ones is an output for a specific line. So again, this one just tells us what variable it is that we're feeding, and this one is telling us what's the actual value of the score, the intercept, and the coefficient. And let's just do that for all of them, because we already know the values, but we can just do it. And again, we could do this in a for loop probably, but this approach works for now. You can see for Indian res, it's this one, and that's the model intercept and the coefficient. This is for the A-tot model. Notice how it's different as well. And finally for the A-dot model. And recall, these are different models. That is why they have different values. So something I want you to notice is we're going to first take this line here and compare the first linear model, that is the one fitting in persons. That is the intercept. Now, what if instead of doing it the first linear model, we do the general one? This one is the one that was fitted on all the variables together. That is the main difference. These are models that have been fed only one predictor into the prediction of these fatalities. But this one was fitted on all of them. The intercept is not the same. It is very close to be the same, and we will look into why that is later. But it is not the same. This one is a little bit higher, and this one is the one that was only fitted with persons. And this is something you want to be aware of in linear regression. When you fit one more variable, you may see your coefficients changing. And yeah, that is just because of the nature of linear regression, how it's fitting to the hyperplane. And again, we'll look at that later. That's a little bit of a difficult concept to visualize without a graph, but I will do my best to explain it. Let's just go ahead and we will do the predictions. Again, this just puts it into format that the scalar can take. In the case of the full linear model, we just need the whole x. That's all we need. In these other cases, we actually need to specify the variable and say reshape it so a scalar can take it. Here we're predicting, if we just take a peek at that, these are the predictive fatalities based on each of the models. So this one is for the first model. The fourth model is here. You can see that they are different. And the full model is somewhere over here. Now, I, again, just prefer you to have a picture to see. So I will go ahead into plots instead, and we're going to plot it. I have walked through this code multiple times, and we're going to be using it a lot of times. But if you have forgotten, first, these lines here are just for aesthetic purposes. This has a title, this adds something in the y-axis, this has the title in the x-axis, and this one just tells us what style you want. The important part here are these two lines here. TLT scatter gives you the scatter plot between persons and y, our response, and it's going to plot them points with a blue color. PLD plot is going to give us the actual regression line using the first predictions to build up the line in a black color. So if we just take all of this, there you go. Why is the score so poor? You can see it actually here at the first glance. This data might be continuous, but there are no decimals there. And actually, it's not actually continuous because of how many variables you can have. It is actually discrete. One half person cannot die. That's why you have nothing in the halves. One half person cannot be involved in it. There is some correlation though. It does seem that Then when you have more persons involved in the accident, you're going to have more fatalities. That is a fair statement to make. But here you can see that this is not the best data for the regression model. Just because on the values and how few possibilities you have, it does not act as an actual continuous variable, but just as a ton of discrete variables that you put together because of the number of persons. We can do the same. In this one is the Indian reservation versus fatalities one. Now, this one is even worse. This is a dummy variable. It seems that there is more people that actually die whenever there is in an Indian reservation, but it is very, very minimal. And this is why this contributes a little bit to the multiple regression model, but not by a lot. For the third model, though, let's see. This one is even worse. There is really, the regression line is almost flat. There is almost no relationship there. And actually, if we were using stats models, we can actually test to see if the relationship is statistically significant or not. But we cannot do that in an easy way in a scalar. Just be aware of that. We can just look at the plot and say, yeah, it looks like there is not really a strong relationship between the two. Let's go to the fourth model, the time of the day of wake instead. Again, not really a lot here. It seems almost the same as the third plot. There is a little bit of difference, but not a lot. So same thing. This one seems to at least contribute a little bit to the model. These two do not. Now, we can compare the results of the regression line of the full model that we feed in everything with a simpler Pearson's model. And we can see the results here. What I'm doing here is the same as we have done before. However, in this case, I am taking the first predictions, drawing a line with them, and also putting the multiple linear regression model predictions. Let's go ahead and do this. You can see our black line, that is the simple linear regression model predictions. And see this orange line, you might be thinking, I thought linear regression was linear because it was a line, right? It's only allowed to be a line. It's supposed to only give me lines. To some degree. There is a concept called the hyperplane that basically linear regression would always fit an n-1 dimensions plane to the data that you're feeding. When we're already in 2 dimensions, this is easy to understand because there is only 2 dimensions. You're feeding on only your x and y, and the line is just 2 minus 1, 1. It's a one-dimensional line. That is why it's called linear regression. But in higher dimensions, it's a little bit harder to understand, more so because of this glitter that the model is doing. Let's make this graph cleaner instead. We can just take the points. So instead of making it a line, we can see the points here. If we were able to see the Indian reservation 3D plane as a z-axis with fatalities and persons, we could see that this is not a line, the orange ones, but it's a plane. It would be a plane, something like this. I would just let you use your imagination, but this is just a 2D projection of a 3D object. It is still linear, but with those two predictors against the predictor. And this is another reason why you might want to just see, kind of why use a simpler model, not only because it's less computationally intensive and it will be faster, but also because even linear regression, one of the most basic predictive models out there, can become really complex really quickly sometimes, more so when you're adding a ton of different variables all over the place. And this is just because this is just a general statement. If you are going to get similar results between two models, one being way more complex than the other one, you want to use the one that is less complex or more simpler. just because it's going to be easier to understand and it's going to be faster as well. Now, we already saw that these two variables are the most important on the model just because of our plot diagnostics. Let's just go ahead and we're going to do the same thing. We're going to create a new model that only fits persons and Indian reservation. And we're going to fit that into those three variables. So we have persons and Indian reservation as our X and fatalities as well. We are going to store these predictions in this two-bar predictions variable. And now we can just plot the model. We have done the same thing as before. The only difference is that we have done two-bar predictions here. And we are still only visualizing this into the persons. Why? Why persons and why not Indian reservation? Because as you have seen here, Indian reservation is a little bit trickier to understand here. We could do it, it's just not the point because this variable is way less important than persons. We run this. Now here you can see better than here or here why I was talking about this plane here. There is this plane, if we could plot in a 3D model, you could see it better. But this plane of predictions is being built instead of an actual line. And this helps the model taking all those predictions and just making it to predict one prediction here. Now, let's just go back to the last part of this video. We can get these predictions in different ways. Let's say that we have this new observation for this MP array. There were 17 people involved in this accident. It was in an observation. It was at night, that is represented by 2, and it was also on a weekend, that is represented by 2 on the 8-hour variable. We saw that. And now we basically try to do this with predict, and we're going to use a different one. This is reshape 1, -1. We can compare this if we go back to our code a little bit to reshape -1, 1. This is just how sklearn ingests the code. You do not need to know the reason behind it. If you want to, though, there is a ton of documentation on sklearn and why it follows that syntax. Let's run this. And this is the array that we get. It's just one value because it is just one prediction. 2.43 people are predicted to die in that accident. But we can do that manually too. We don't need to rely on predict. And if you have seen the linear regression formula, this is going to be very, very familiar. You take your intercept, then you add to that your first coefficient of your first predictor times that predictor value. Then you add the second one times the value of the second prediction, and you so on and keep going until you have exhausted that. This is what sklearn is doing in the background. And it's just good to understand it because this is how you apply statistical models to programming languages. Something that you may know as and data computing. There is a ton of names for this. But this is one of how you can do it. Some people also call it how you model statistical models into programming languages, etc., etc., etc. Computational science, etc. You may know it for different names, but this is how you're applying a statistical model into a programming language here. And I will say, even though you can do this with these two, as in predict here, this predict saves us a ton of time instead of doing this, but we can still do it. And we can sprint this. It is exactly the same value because it was calculated the same way. Now we can compare these results to the first model. Honestly, remember that this is how many people died. If you were to give these two models to a police department or office, for example, they will probably just either round it up to 3 or run it down to 2. But we have seen that there is not a lot of difference in the predictions. The other variables are very, very bad at predicting how many fatalities happen. And as you can see, even persons is not a good indicator of how many people are going to die. What I'm trying to say with this, if you were given the case of we still need to use one of these models, and for some reason we just stuck with linear regression, you would just go to the simpler model, the one that you are just fitting on persons. Because again, a simpler model is just better most of the time if you are not going to get a better result by fitting more variables or doing more complex things. And even if linear regression does not fit this data very well, it is a good exploratory data analysis tool. After doing all of this, we know the relationship of these variables. We may say to whoever is requesting us to do this, there is really no relationship between the fatalities and the time of day, for example, or the fatalities and the day of week. We can see here, there is no reason why we may want to do this instead. Also, regression models are one of the easiest and more interpretable models. As you could see here, it's nothing more than a straight line or plane when you are adding more variables to the multiple linear regression model. But it's a very good tool to evaluate your assumptions and your data. We have plotted the data and we know how it looks like in most of our variables here. We also have done the scatter plots, so now we just have done the scatter plots as well as the regression line. And that is where I'm going to finish this video today. Again, sometimes just a simpler model is better. And even in the case of regression, sometimes just fitting one variable is good enough. As always, like this video if you like it, comment this video, share it with your friends. I will appreciate any support. And I will come back with some more videos. Thank you very much. Have a good day.